Okay, so tomorrow is the problem session at 1:30, and in the problem session I'm going to first of all answer questions and then do some of the topics that are in chapters, say, 9 through 16. So, for example, there was some interest expressed in Monte Carlo methods, which I discussed briefly in the last problem session. I'll go over Monte Carlo methods, I think, in a more detailed way in tomorrow's problem session. But if you have questions about the complex variable theory, I can certainly do that instead. Now, as I said to you, let's see, your homework is here down somewhere. I just misplaced it. There. As I said to you last time on Monday, the nice thing about these two from this, the nice thing about one nice thing about complex variable theory is that everything, the main results are very simple, and they follow simply from the definition of analyticity and differentiability. And so the idea is that f prime of z is the limit as z prime goes to z of f of z prime minus f of z divided by z prime minus z. And the important thing is here, from all directions. So the point is that whereas in real variable theory, the derivative is just that you let x prime approach x, either from positive or negative directions. Here, z prime approaches z from all directions in the complex plane. So this is z, and z prime comes in any which way. The limit has to exist no matter how z prime approaches z. And an example of an analytic function. So anyway, if this is, the function is differentiable at z if this multiple limit exists. If it's differentiable in a certain area in a disk around z, then it's said to be analytic at z. And the function that's analytic everywhere is the polynomial of some Cn z to the n equals 0 to some capital N. And we then derived from differentiability and analyticity the Cauchy's integral theorem, which says if you have a region here R that is simply connected meaning no holes, and a function f of z is analytic here, analytic in R, then the integral along any contour of f of z is dz. dz is equal to 0, and this is true for any closed contour inside that lies wholly within the region of analyticity. And I must call your attention to the fact that if you had a region of analyticity that was not simply connected, that had a hole here, then the contour integral, when a contour integral went around the hole of an analytic function, may or may not be 0. It depends. And if the function is not analytic at some points inside the hole, then this, in general, this contour integral would not vanish. That was Cauchy's integral theorem, and we proved it by directly from the definition of differentiability. First for a small circle, then for a small square, and than in general. And then we derived Cauchy's integral formula, which is that f of z is equal to 1 over 2 pi I integral f of z prime dz prime over z prime minus z. And that's Cauchy's integral formula. And then effectively by differentiating that integral formula, we get an extended version of Cauchy's integral formula, namely that the nth derivative at z is n factorial over 2 pi I. Integral any contour that goes around the point z in a counterclockwise way, f of z prime dz prime, now over z prime minus z to the n plus 1. So that's Cauchy's integral formula. The right, I don't. I'm terrible with names. I'm really sorry. Do you already have yours?
No, it's probably in the mailbox.
Oh. Well, it might have been in the mailbox even yesterday, because I got these yesterday. I just didn't know it was on the class. Okay, so this is the Cauchy integral formula. And then, moreover, we saw that if a function f of z has a real part u and an imaginary part v, then the real and imaginary parts will satisfy the Cauchy-Riemann conditions, which are u sub x is equal to v sub y, and u sub y is minus v sub x. And we derive these directly from the condition of differentiability. That is to say that the limit exists whether you come at it from the x direction or the y direction or the other direction. You can use x and y. And it followed from this that u and v are both harmonic, and in fact, that is to say that uxx plus uyy is 0, and that vxx plus vyy is 0. Subscript x means d by dx, subscript y means d by dy. So these are two-dimensional Laplacian on u and v vanishes. All right, I'll come back to that in a moment. Let me go back now to the Cauchy-Riemann conditions. Just, anyone have a question about the Cauchy-Riemann condition? Sometimes when I teach this course, I carry candy. And oh, here, I forgot to give you guys a. Somebody want to catch this? Good catch. In fact, not only are these these Cauchy-Riemann conditions not only imply that the function is harmonic, but they also imply that the two-dimensional gradient of u dotted into the two-dimensional gradient of v, which will then be u sub x, v sub x, plus u sub y, v sub y, that this is equal to 0. And why is that? Well, v sub x is minus v sub y, so this is minus ux uy, and then v sub y is u sub x, so this is that plus u sub y, u sub x, so that's 0. So the gradient of u dotted with the gradient of v is 0. And the situation then is that if you look at surfaces of constant u, it might be like this, u equals c, then surfaces of constant v are perpendicular.
My bad.
V equals D, say. Oh gosh, was that the whole supply?
Yeah.
Well, fortunately, there's some left over from yesterday. Here, why am I?
They need to go that way.
Okay. Now, these Cauchy-Riemann conditions and a two-dimensional version of Stokes' theorem provide an alternative proof of Cauchy's integral theorem, namely that the integral of f in a region of analyticity vanishes. What one has basically is that the integral along C of E dot dr is the integral on the surface of curl of the dot dA or ds. And the idea is that if this is the contour looks like that, you put your fingers in the direction of the contour, and then your thumb points more or less in the direction of the outward normal. But you see, to a surface, there are always two normals. That is to say, two perpendicular to the surface. The one in the direction of your right-handed thumb is the one that you want. That's the dA or ds. In any event, what I want to do now is consider an integral of a function f of z, dz, around some contour c, but I'm not going to assume that the function f is analytic. And so what we'll find is we get an expression for this integral, and we'll see that when the Cauchy-Riemann conditions are satisfied, the integral vanishes. When they're not satisfied, then we have simply a formula for this integral, which can be useful actually, and I'll show you an example of that. Before doing that, though, let me actually just insert something in here. Suppose f of z is a polynomial, so that it's a sum cn z to the n up to n equals 0 to n. Then that's an analytic, that's an entire function. And if we integrate this around some contour, we're going to get 0. And in particular, if I choose as a simple contour just a circle about the origin, so that z is equal to some capital R e to the I theta, then this thing is an integral c sub n, well, some c sub n r to the n e to the I n theta, and now we're integrating around the circle, so let me get an eraser. All of them red out. So this is, so dz is I r e to the I theta g theta, and so this is an integral 0 to pi I r e to the I theta d theta. Well, you can see that even the term with n equals 0, so this is then the sum n equals 0 capital N Cn r to the n plus 1 and overall I equals 0 to 2 pi e to the I n plus 1 theta d theta. Well, these integrals all vanish because even for n equals 0, because you have at least the integer up here is at least 1. And so explicitly, this integral explicitly is e to the I n plus 1 theta evaluated at 2 pi and 0 divided by I n plus 1. So that's just an example of Cauchy's integral theorem. But now let's consider a case where f is not necessarily analytic. And so, and what I'll be going through will be essentially a proof of Stokes' theorem for this two-dimensional case. And so we're going to have an integral of u plus iv. And now what is dz? Well, that's du plus, I'm sorry, dx plus I dy. Okay? That's the integral that we're talking about. And in particular, that's going to be an integral of u dx. I guess I have it written one way in the notes, but I think it's probably easier for you if we write it this way: u plus iv dx plus integral I u plus iv dy. Let's look at one of these integrals now, the integral u dx. So what is this? Well, I want to draw a picture here. So let's just look at the contour. Let's suppose it's a kind of boxy contour, just to make it a little bit easier. So we've got here an integral here, dx, and then straight above it, we've got another integral dx, but the dx here is negative, the dx here is positive. The value of y, in fact, what is this integral? It will be an integral then of u of x, y minus of x. That's y minus is the value of y associated with x on this curve, and y plus of x is the value of y up here associated with x. Okay. So this thing is u of x, y minus of x, minus u of x, y plus of x, and then all this dx. Okay, now, why don't you look at that and let's ask a question about it. Somebody have a question? Okay, we have a curve here in the complex z plane where z is x plus iy. So for every x, there are two y's. Y minus of x is here, y plus of x is there. Okay? So this value of x, y minus of x is here, y plus of x is there. Okay? Where here we've got this is the z plane, so we can have this the x-axis, this the y-axis. Okay? All right. Now, the difference of these two is just minus the integral. So this is just minus the integral, minus 1, say, times the integral. And let me look at the notes. Minus y minus of x, y plus of x, of u sub y of x and y dy. Dx. In other words, this square bracket is equal to that square bracket. So although I'm not assuming the function f is analytic, I'm assuming that the part that it has a real and imaginary parts that are at least differentiable with respect to x and y everywhere. So this is what we have. And now you can see you have an overall minus sign, but now dy and dx are both positive. We took into account the negativity of the dx there with this minus sign. So now dx dy is positive. And so what we've got is that this particular thing then is an integral over the surface of u sub y of x and y dA, where dA here is just the absolute value of dx dy. So that's what one of those integrals is. And now we have three others, and you can check for yourself that I integral v dx is equal to minus I integral c sub y dA. When I say dA, I mean over the, in other words, this contour, if this is the contour, then we're integrating, the surface integral is over the area enclosed by the contour. Similarly, the y integrals, well, the y integral around v has two i's, so that's a minus sign. So minus the integral c dy.
Don't worry about it.
You're sure it's analogous?
Yeah.
Good. I hope you're right.
I'll leave if I start to feel queasy.
What?
I'll leave if I start to feel queasy.
Yeah.
It's too late.
Well, actually, it's worse than that. Apparently, after a person recovers from, if one recovers from pig flu, one is still infectious for 1 or 2 days after the symptoms disappear. It's a lovely disease. The last term is integral around the contour of u dy. This is I integral u sub x dx. You use the same logic to do all of these. So then we have the following result. Maybe I'll write it here. Integral u plus iv dx plus I dy is minus the integral of uy plus vx dA plus I integral, I should write it as ux minus dy, I think, dA. And it's the integral over the area included, the area that's circumscribed by the contour C. Now, what you can notice is that if the Cauchy-Riemann conditions are satisfied, this explicitly vanishes. Both integrals are 0, because the Cauchy-Riemann conditions were u sub x equals v sub y, so then this term would be 0. And then over here, it's u sub y equals minus v sub x. So if the function is analytic, explicitly this integrand vanishes and this integrand vanishes at every point inside the contour. So then you get completely 0. On the other hand, if you have a function that's not analytic, then you have to basically do the integrals. And now sometimes the function you're integrating is what you might call quasi-analytic. In other words, it's kind of analytic, but there's part of it that isn't analytic. In that case, by writing the line integral, the contour integral, in terms of these area integrals, what you'll have is you'll have a big cancellation in here, because the part of the function that's analytic will cancel. And that's done in an example here. Oh, before I get to that example, let's just look at what the absolute value of this thing is. So this is strictly 0 if the function's analytic. Otherwise, it's the integral of ux plus vy dA, absolute value squared, plus absolute value squared of the integral ux minus vy dA times phi squared. So it's equal to these things, and these things here, of course, u and v, being real imaginary parts, these are real functions. All right, so let me take as an example of this the function f of xy equal to 1 over x plus iy plus I epsilon, and then 1 over 1 plus x squared plus y squared. So this is a function in which the first term is analytic. There's a pole at y equal to minus epsilon and x equal to 0. But apart from that, the function's analytic. And so it's not analytic. This part is analytic. This part is not analytic, because x squared plus y squared is z bar, and z bar is not analytic. All right. Okay, so what are the real imaginary parts here? Well, u of x and y is then equal to u, little u of x and y, times r of x and y, where I'm going to be using u. This function is 1 over z, so I'm writing this as u plus iy. Let me see how I'm writing this. Okay. I'm writing this as u plus iv times r. R is this thing. And u we remember how you rationalize something like that. 1 over z plus I epsilon, we can multiply by the complex conjugate of that in the denominator. And so what we get is x squared plus y plus epsilon squared. And in the numerator, we simply get x. So that's the real part. And then the other part is plus I, and then here it's minus y minus epsilon over x squared plus y plus epsilon squared. So that's how we rationalize 1 over z plus I epsilon. Is that clear, or would you like me to fill in the steps? What you do is you just multiply top and bottom by z star minus I epsilon, z star plus I epsilon.
And you should still have the 1 plus x squared. Oh, you left out r, sorry.
Yeah, I'm leaving out r. I'm just doing the first term, because I'm writing the first term as u plus iv to make use of its analyticity, and then I'm just using r for this thing that's remainder, so to speak. Okay, so this big U then is equal to x over x squared plus y plus epsilon squared, 1 over 1 plus x squared plus y squared, and then v of x and y is minus y minus epsilon over x squared plus y plus epsilon squared, 1 over 1 plus x squared plus y squared. Okay, so that's what we've done. And v is equal to little v r. Okay, so our integral I is the conjugate integral of f of x and y dz. And what's the contour? The contour in this case is going to be along the real axis from minus infinity to plus infinity, and then around the upper half plane, like this, where we go, in other words, from minus r to plus r, and then over here we go r e pi theta, where theta goes from 0 to pi. Okay, so this thing is then an integral minus infinity plus infinity dx. And it's effectively an integral. The contour integral is what I just showed you. By our theorem over here, that's an area integral, and the area enclosed by the contour is the whole upper half plane. So this is equal to the integral 0 to infinity dy. This is the area integral. And what do we have left? Well, it is by using this theorem that we just proved, namely that the integral of f of z dz is this area integral plus that area integral. What we have here is minus u sub y minus v sub x plus I minus v sub y plus u sub x. So that's our area integral. On the other hand, minus u sub y minus v sub x turns out to be just minus u r sub y minus v r sub x, because the part that involves derivatives of the analytic function cancels. So we get quite a simplification. And minus v sub y plus u sub x is then minus v ry plus u r sub x. And the sub x sub y means partial with respect to x, partial with respect to y. So that's what we have. So in other words, this integral I is simplified considerably, and we have I is equal to integral minus infinity plus infinity dx, integral 0 to infinity dy, minus u r sub y minus v r sub x plus I u r sub x minus v r sub y. And explicitly, that's minus infinity plus infinity dx, 0 to infinity dy, and that's minus 2 epsilon x minus 2I x squared plus y squared plus epsilon y, all divided by x squared plus y plus epsilon squared, 1 plus x squared plus y squared squared. If we let epsilon go to 0, and we were always thinking about letting epsilon go to 0, then this simplifies to minus 2I integral minus infinity plus infinity dx, integral 0 to infinity dy, 1 over 1 plus x squared plus y squared squared. In other words, we've had this term canceling this term in the limit. Epsilon goes to 0. And this term goes away. So it's simplified a lot. We can do this integral in cylindrical coordinates. And, well, polar coordinates, I guess. And this is then just minus 4 pi I integral 0 to infinity d rho over 1 plus rho squared, and that is 2 pi I integral 0 to infinity d rho of d rho 1 over 1 plus rho squared, and so that is 2 pi I 1 over 1 plus rho squared evaluated at infinity and 0, and so that just gives us 2 pi I. So that's, wait, I've got a minus sign loose here somewhere. I have minus 4 pi I here. Oh yes, it's a minus sign when you differentiate, so that's a plus, and and there's a minus here. This is a lower limit, that's possible. Okay, so that's an example of a case of where Cauchy's integral formula simplifies a contour integral because the function is partly analytic. All right, harmonic functions. So we saw that the real part and the imaginary part of an analytic function is harmonic. That is to say, uxx plus uyy is 0, and vxx plus vyy equals 0. And this means that a harmonic function can have no minima or maxima, because at a minimum you have all the derivatives look like that, and consequently the curvature is positive in the x direction and in the y direction, and so you have uxx plus uyy greater than 0 for a minimum, less than 0 for a maximum, and the same thing for v. And so for a harmonic function, you can never have a minimum or a maximum. And so we can now have an application to electrodynamics. So I'm thinking here of electrostatics, and in electrostatics we have the potential phi of x, y, z is such that the electric field is minus the gradient of the scalar potential, and here I'm thinking that we're in a vacuum, so we don't. Well, this is actually still true. You can have a dielectric. Anyway, and if we are in a vacuum, then the divergence of E is 0, and that means that minus grad squared phi is 0. So that means that pxx plus pyyy plus pzz equals 0. So that's Laplace's equation for the scalar electrostatic potential, and that says that the electrostatic potential is a harmonic function of 3 dimensions. Now, and since it's harmonic, it cannot have minimum or maximum. Now we're talking 3 dimensions, and the reason here is that you need to have. Hey, I was slightly wrong here. The condition for a minimum is that both of these are positive, and for a maximum that both of these are negative. Here you have to have that this was either this greater than 0, that greater than 0, and that one greater than 0, or this one less than 0, this one less than 0, and that one less than 0 to have a maximum. So the harmonic function in 3 dimensions is a minimum or maximum is absolutely out of the question, and this has a practical consequence, namely that you can't use electrostatic forces to confine particles. In other words, you think just offhand that that a charge follows an electric field, so you can arrange an electric field so that you get the electric field to push the particle to a particular location. But in fact, if you're in the vacuum and you have the Laplace's equation, this is equal to 0, then you can't have a minimum of the potential. So you can't localize a charge with an electrostatic potential. And so people who do localize ions use magnetic forces as well as electrical forces. Okay, so this is called Earnshaw's theorem. All right, now let me just now, the real electrostatics, of course, occurs in 3 dimensions. We've turned off the time variable because we made it static, but otherwise it's still 3 dimensions. However, there's a certain class of electrostatic problems in which the z, in which there's no dependence on one of the variables. So, for example, you might have a line charge that's uniform in the z direction. Or you might have a cylinder, a charged cylinder that's uniformly charged in the z direction. Or you might have any sort of conductors or arrangements of charge, and even dielectrics for that matter, that simply don't depend upon z, but only depend upon x and y. And in that case, the potential has to satisfy the 2-dimensional Laplacian, because nothing depends upon z. It satisfies the Laplace equation in 2 dimensions, and that means that the real part of any analytic function is a possible potential, and the imaginary part is a possible potential. So all of a sudden you've got basically the solutions to all of those electrostatic problems are just the real and imaginary parts of all of the complex, all of the analytic functions. And we learned over there that u and v had perpendicular gradients. That is to say, grad u dot grad v was 0. Well, if you say that the electrostatic potential is u, then the electric field is minus grad v, which is to say minus grad u. Then the gradient of v is perpendicular to that. But what's perpendicular to the electric field is the equipotential. So u equal to a constant. Oh, I'm sorry, v equal to a constant. No, u equal to a constant is equipotential. VE, the electric field, is perpendicular to u. It's perpendicular to the surface u equal to a constant. And that's the electric field. So in other words, we have here u equal to a constant is the equipotential. V equal to some other constant is the lines of the electric field. And they are perpendicular to the equipotential surfaces. All right. A couple of examples are called for. So let me give you the simplest example is you take the function f of z and you just say, well, this is easy. Okay, this is a very easy example. It's just ex plus I ey. Well, in this case, the potential v of x, y, z is equal to simply ex. So that means you've essentially got an electric field pointing in the negative x direction. So E is pointing that way. And so if you move a positive charge this way, the potential energy rises. So the xy plane, V, would look like this. And then what about y? Wait a minute now, what am I doing? V, no, that's V as a function of x. But if we look in the xy plane, then what are the equipotentials? Well, the equipotentials are the lines of constant x. So these are the equipotentials. So this is V equals, if this is x1, this is V equals EX1. Here we have V equals EX2, or x2. On the other hand, the other thing, V, which is equal to EY, that is the lines of constant V are these lines, and these, of course, are the electric field lines, because the electric field points in the negative x direction. So these are the lines of electric field. Okay, so that's an example that's fairly simple. A slightly more interesting example is x equal to z squared. Well, then this is x squared minus y squared plus 2i xy. And now u is x squared minus y squared, and v is 2xy. And so this function, this analytic function, gives us a potential which we can take as v of x, y, z as proportional to x squared minus y squared. These are hyperbolas, and in fact they look like this. So these are the hyperbolas, and if we set that equal to the potential, then, in fact, these hyperbolas are the hyperbolas that are given by v equal to x squared minus y squared is equal to c squared. So x squared is equal to c squared plus y squared. So this is c, and that's minus c. And so these are the equipotential surfaces. So that's the v equal to some value, I don't know, what do we call it, v1, and then we'll have these hyperbolas, v equal to v2. And now the other equation, little v equal to a constant, would be v equal to 2xy equal to some constant d. Well, these are also hyperbolas, but these hyperbolas, you see, look like this. And notice that these electric field lines are perpendicular to the equipotential surfaces, as they must be, because electric field lines are always perpendicular to the, well, I didn't draw the thing correctly, but you can see how it works out. All right, any questions? Third example, I'm going to use z equal to r, e to the I theta, and the function is going to be f of z is u of x and y plus I v of x and y. And I'm going to make this be minus lambda over 2 pi epsilon 0 natural log of z. Wow, we can typos here. Which is to say, minus lambda over 2 pi epsilon 0 log of the absolute value of z plus I theta. So I'm anticipating we're going to be studying the logarithm in a week or so, and we'll understand that the logarithm is analytic but multi-valued. And what do I want to say? So for now, we can just say that it's analytic but multi-valued. So it's an example here. This describes the potential v of x, y, z equal to minus lambda over 2 pi epsilon 0 log of r being the distance from the z-axis, which is to say square root of x squared plus y squared. So that's the potential, and that is physically the potential of if you have the z-axis charged with a charge density lambda equal to q per unit, q coulombs per unit length, and the electric field lines E are lambda over 2 pi epsilon 0 x, y, 0 over x squared plus y squared. So if we look down, if we're just looking in the xy plane, then the electric field lines are radially out. They are perpendicular to the equipotentials. The equipotentials are simply circles around the origin. And what else? I guess I've probably milked that as much as I can. All right, so those are a few examples. So you can do amazing things if you have two-dimensional electrostatic problems. For some reason, Jackson doesn't cover this. I don't know why. But there clearly are examples where you have two-dimensional, where you have electrostatics only in two dimensions. And for example, if you just have any kind of a pipe for any kind of radiation, then it's a straight pipe, and the variable in this direction drops out of the problem, and so these methods would be applicable. Of course, it's for electrostatics; you don't get all of the electromagnetic. Also, I must say, it took me some trouble coming up with these examples, actually. It's kind of counterintuitive. So if you want to come up with your own problems or own examples, I mean, you could, for example, take F equals Z cubed. That will give you another kind of family of potentials and equipotentials. By the way, in this case, you can always, I forgot to mention this, but if you can either take U to be the electrostatic potential and V to be the other thing. That is to say, if U equal to a constant is the equipotentials, then V equal to a constant is the lines of the electric field. But you can also do it the opposite way. You can take V to be the potential, and then U becomes U equal to a constant is the lines of electric field, and V equal to a constant is the equipotentials. Maybe you should turn that thing this way.
Yeah.
Okay. Any questions before we go to Taylor series? All right, the Taylor series. This is again an application of Cauchy's integral formula, which, as I said to you, follows directly from the definition of differentiability. So the cleanness of the logic is one of the things that attracts people to this field. So we have 1 over 2 pi I integral f of z prime dz prime z prime minus z, and this is, remember, this is for, we have some region R, and it's simply connected to the region in which f is analytic, and then this thing is any old contour C in this, and we're going around the contour in a counterclockwise way. That's the convention. It gives you a plus sign there. If you went around the other way, you have a minus sign. All right. Well, what we're going to do is we're going to pick a point Z0 here. And in fact, what we're going to do, I mean, this is true for any contour about the point Z, any contour that encloses the point Z. So Z here at some point inside that contour. But now, to make the geometry simple, what we're going to do is we're going to choose this contour to actually be a circle. Not centered in Z, though. It's just an arbitrary circle. And the center of the circle is going to be Z0. So we have Z0 as the center of the circle, and that's going to be our integral. Okay, so we now rewrite it in terms of Z0. We could Zorro. Anyway, f of Z prime dz prime. And now we write Z prime minus Z0 minus Z minus Z0. So I've just added and subtracted Z0. And now we can factor that denominator. and we write it as z prime minus z0, and we write this then as 1 minus z0 over z prime minus z0. Okay. All right, now let's note the magnitudes of these things here. Z minus z0, since z is inside the circle, and this is a circle, z is closer to z0 than any of the points z prime. Because the magnitude here of z prime minus z0 is equal to the radius of this, well, I don't want to use r twice. Let's use little r. Is the radius of the circle, whereas, and that's greater than z minus z0, because z is inside the circle. It's not on the boundary, it's inside the circle. And now we use one of these little formulas that was, remember when we studied power series, I said, well, it was one of these power series was really useful. Well, they're all useful in some way. But one of the ones that's particularly useful is 1 over 1 minus epsilon. This is the sum n equals 0 to infinity epsilon to the n, as long as epsilon is less than 1. And epsilon can be complex. So that means that we can rewrite this thing. Now, epsilon in this particular case is z minus z0 divided by z prime minus z0. And clearly, the actual value of epsilon is less than 1. So we can rewrite this as 1 over 2 pi I integral the z prime dz prime over z prime minus z0. And now we're going to have this as a sum n equals 0 to infinity z minus z0 over z prime minus z0 to the n. So this is just this formula. All right. Now remember, this thing converges uniformly and absolutely. And so we can do this integration, contour integration, term by term. And what we're going to be getting then is the sum, n equals 0 to infinity. We can bring out the z minus z0 to the n. 1 over 2 pi I. Integral around the circle. F of z prime to z prime. And now we've got z prime minus z0 to the n plus 1. Okay, now we invoke Cauchy's integral formula, which follows from this as Fn of z is n factorial over 2 pi I integral f of z prime over z prime minus z to the n plus 1 z prime. In that case, our formula here is 1 over 2 pi I. Well, how the 2 pi I goes. It's just a sum n equals 0 to infinity. The nth derivative at z divided by n factorial, because that's this n factorial. So in other words, this integral over 2 pi I is just an nth derivative over n factorial times z minus z0 to the n. So I'm going directly down from that. This is called the Taylor series. And it converges as long as both points z and z0 lie inside you see, now the circle is gone when we get to this. So this just means that z and z prime z z and z0 have to be within the simply connected domain of analyticity here. So now z and z0 are just 2 points, and because you can take any 2 points and then draw a circle. Let's see. I guess you can ask, what if the thing looks like this, and you have z0 here and z out here. Okay, I'm going to have to think about that. It may be that we need to put z and z0 inside the circle. Or let's say that I proved it only for the case where the circle with center at z0 and going slightly beyond z is inside the region of analyticity. Now, so that's where I proved it for. What happens in this odd case? Well, it depends. I think the thing could break down actually. But you could have some singularities out here, and in that case, this would only work for z that are close enough. So I think maybe I should change. Maybe should trim down the statement to actually what's proven here. All right. Any questions? Yeah.
I guess I'm a little bit confused on that equality you have there.
Which equality?
When you plug in the nth derivative of f into what's above it to get your final series.
Yes.
I guess I'm seeing where everything comes from and goes to.
So we just divide both sides by n factorial, so that's 1.
Yeah, and then so the 2 pi i's cancel out on each side.
Oh, well, the 2 pi I integral just gives you f, the nth derivative over n factorial, and then the only thing that's left is this to the n. So it's nth derivative over n factorial times the coefficient c minus the power of c minus.
Don't you have a? It looks like you have a z prime minus z0 for party refraction.
Brilliant.
A z prime minus z.
Brilliant. I left out a 0. So here, all right. So let me just put in the zeros in both cases. That's great. Okay. That's great. You're absolutely right. I just left out the 0. Any other corrections or questions? That was an important one. I think it's correct. Well, I think I skipped some of the steps in the notes. All right. Any other questions? All right. Let me go to Cauchy's inequality. Suppose f of z is analytic in a region that includes the disk z, the circle z equals r e to the I theta, and everything inside, and assume that the absolute value of f of z is less than equal to m for z equal r. So in other words, we've got this circle about the origin, radius r. On that circle, f is bounded, and f is analytic on the circle and inside the circle. Then we can use Cauchy's integral theorem, integral formula, I mean, to compute the derivative at 0 at the origin, and it's less than or equal to. Well, maybe I should say what it's equal to, and then get to the less than or equal. So in absolute value, it's equal to the absolute value of n factorial over 2 pi I integral f of z dz over z to the n plus 1. It's that absolute value, and that's less than or equal to n factorial over 2 pi, the integral of the absolute value of f of z dz over z to the n plus 1. And remember dz, since z is equal to that, dz ir d theta d theta. And so this is less than, and f is less than or equal to m then, so we have n factorial m over 2 pi. We have an integral 0 to 2 pi. This is r to the n plus, this is actually equal to r to the n plus 1. And then we're doing r d theta. The d theta integration gives you 2 pi. And so the answer is n factorial m over r to the n. Okay. So that's what the n derivative at 0 is bounded by if the function f is analytic in the disk of radius r and bounded on the periphery by capital M. All right, I could push on a little bit, but I think maybe we've been moving fast enough. I'll just stop here. The next topic is Liouville's theorem, and then after that, the fundamental theorem of algebra, which is what I promised you when we were doing the linear algebra stuff. I'll try to put the next homework assignment up, and in fact, I can just tell you what it is. It's just 2 old problems at the end of chapter 4. And so, any questions? And as I said, we'll do something about Monte Carlos, as well as answer questions, but we certainly, there's no harm in answering questions during the problem section.